Dear colleagues, it is my pleasure to introduce my study, theoretical study of the coupled effect of sample size and strain rate on the tensile strength of log-like material. My report includes the following parts. The first part, introduction. The temporal spatial effects on local strength includes size effects, meaning decrease of strength with the increase of sample size, and the strain rate effect, meaning increase of strength with the increase of strain rate. As to size effects, there exist several models. The first, statistical model, described by Wimber's theory of random local material strength. The second, type 1 size effect, energetic or deterministic nature, occurring in the fracture caused by the Planck initiation on smooth surface of sample. The third, type 2 size effect, occur in the materials with a deep notch or deep strength-free grain formed stamply before reaching the maximum loading. The first model based on fractal or self-similarity concept. As to strain rate effect, many scholars have conducted in-depth research on the phenomenon experimentally and theoretically, but the research on the coupled effects of sample size and strain rate on strength of log-like materials is limited. Study of Hong et al. On several kinds of log and compression revealed that the dynamical strength of log increases according to the power law with the increase of strain rate, and the same strain rate, the dynamical strength of log increases with the increase of specimen size. For specimen of certain size, there exists a critical strain rate below which the statistical size effect dominates. For a given strain rate, there is a critical size. When the sample size is larger than this size, the dynamical size effect is dominant. Qi et al. Explained dynamical size effect observed in Hong et al. Qi et al. Revealed that the essence of the strain rate effect is that the deformation and fracture process of small-scale elements in sample are activated before the complete breaking of sample, with the increase of the strain rate due to the finite grain propagation speed. Asadi et al. Studied the combined effect of loading rate and sample size on tensile strength, and revealed that the notched specimen is more sensitive to the loading rate. There exists a critical strain rate at which the specimen size had no effect on the specimen strength. When the loading rate is greater than the critical loading rate, larger tensile strength is observed as the specimen size increase. This figure shows the experimental data. Remarks. The current research on the coupled effect of sample size and strain rate on strength of quasi-brittle material were basically experiments. Some formulae for the coupled effects of sample size and strain rate on strength were obtained by data fitting. The physical meaning of the obtained data fitting formulae is unclear. Thus, the underlying physical mechanism of the coupled effect of sample size and strain rate on strength is not clear. Therefore, the purpose of the study is to quantitatively predict the nominal tensile strength of log mass with different size and different strain rates, to clarify the underlying physical mechanism of coupled effects and strain rate effect. Part 2. The coupled effects of sample size and strain rate on tensile strength in quasi-stable regime. The dynamical tensile strengths include two parts: the thermally activating strength component and the quasi-static loading, and the microscopic viscous components and dynamic loading. In the following, we examine the two parts of strength. And the quasi-static tensile loading. Deformation and failure of material is thermally activating process. The expected lifetime of material can be determined by Joule-Kerfels formula, in which U0 is the activation energy, sigma T is the uniaxial tensile strength, gamma is the activation volume, K is the Boltzmann's constant, T is the absolute temperature, tau 0 is a temperature parameter in the order of Debye's vibration period of atoms. From equation 1, we can obtain the dependence of strength on strain rates as equation 2, where sigma dot is the characteristic average strain rate during loading. Epsilon 0 is the deformation limit at failure. Epsilon 0 dot represents the maximum possible strain rate in the material. If the quasi-static tensile strength test is carried out at the reference strain rate epsilon dot, and the corresponding strength is sigma r, then we have the following expression. Therefore, the relationship between the strength sigma y at arbitrary strain rate and the strength sigma r at the reference strain rate epsilon r dot can be expressed as equation 3, where alpha is the model coefficient. The logarithmic dependence of strength of material on strain rate has been confirmed by many experiments and quasi-static loading. For the sample size effect, the statistical strength sigma r of a material can be expressed as following function of the sample size as proposed by Basant by equation 4, where sigma r0 and dr0 are material parameters. Here, we assume that alpha is independent of sample size. The formula for strength, considering the size effects and the quasi-static loading condition, can be expressed by equation 5. And the quasi-static loading condition, the sensitivity of strength of material to strain rate is mainly controlled by thermally activating mechanism. Sigma r can also be expressed as a multi-fractal scaling law proposed by Capiteri as equation 6, where Fc is the nominal strength of an infinitely large specimen. dCH represents the internal material length. A universal sign effect law for small to large signs was given by Bazant et al. As equation 7, where Fr infinite is the nominal strength of a large size sample. dB, Lp, Ls model parameters. R is a positive constant. N is a dimension scaling the fracture. M is a Wimbor's modulus. Part 3. The coupled effects of sample size and strain rate on tensile strength in dynamical loading regime. Wimbor's theory includes the weakest link assumption. The number n of activated grains in unit volume and action of strength sigma is expressed as equation 8, where sigma 0 is the reference strength. It is the maximum strength considered, corresponding to the minimum grain size considered. Lambda 0 is the maximum number of grains per unit volume, where the critical strength is less than sigma 0. M is Wimbor's modulus. For a disk-shaped crank and the action of uniform tensile strength, the crank propagation on set condition is expressed by equation 9. The critical strength sigma required to initiate crank grease is expressed by equation 10. Number of activating crank in unit volume of material is expressed by equation 11. At the special but common case of m equals 6, we have equation 12, which means that the distribution is proportional to the density of crank of size r. From equation 10, we can see that large size crank are easily activated. With the increase of sample size, more cranks of larger size appear. The upper limit of size distribution increases. Subsequently, the activating large crank will be more. Density of activating cranks of certain size R will be less. To account for the decrease of activating cranks of certain size, with the increase of sample size, we introduce the term d minus theta into the distribution function so that we have equation 13, in which additional parameter theta greater than 0 is introduced. The reciprocal of the crank density A represents the volume occupied by crank, and the cubic rate of the volume occupied by each crank determines the average distance L between cranks at this scale level. It is determined by equation 14, where d1 is a constant. Determine the size R of defects that coalesce first and lead to the final failure of the specimen at the condition of constant strain rate. The propagation initiation strength for the crank with radius R can be determined from equation 10 as equation 15, where K1 is a constant. For constant strain rate loading, the time from the beginning of loading to crank initiation is determined by equation 16. The time required for crank to extend L distance is determined by equation 17. The total time required from the beginning of loading to coalescence of adjacent cranks is determined by equation 18. From equation 18, if its derivative with respect to R equals 0, the size Rc of cranks that coalesce first can be determined as follows as equation 19. The total time required from the beginning of loading to coalescence of the adjacent crank is expressed by equation 20, where d3 is a multi-parameter. So the dynamic viscosity is expressed by equation 21, where beta is a model parameter. The macroscopic viscous component of strength expressed by equation 22. For sigma greater than 0, the dynamic strength increases with the increase of sample size, which is opposite to the statistical size effect law. The dynamic tensile strength includes the thermally active strength components and quasi-static loading, and the macroscopic viscous components expressed by equation 23. Therefore, we have the following three kinds of expressions for the dynamic strength of rock. Part 4. Validation of the proposed model. For quasi-static loading, the term with logarithmic dependence is really weak and can be neglected. For parameter sigma r 0, beta and m and theta, we take in the following values. The completion of the theoretical protection with experiments is shown in the following tables. We can that the agreement is very good. The agreement can be observed in the following figures. The interaction of the two parts in equation 28, it is equation 29, determine the critical strain rate at a fixed sample size and the critical sample size at a fixed strain rate, above which the dynamic science effect dominates. For example, from equation 28, we have the following equation for determining the critical strain rate at fixed sample size and the critical sample size at a fixed strain rate as equation 13. The difference between proposed here model and the model in Asadi is that in our model, the critical loading rate depends on the sample size, and the critical sample size depends on the loading rate. For three kinds of log samples with diameters of 25, 15, and 100 millimeters, we have calculated the critical strain rate and the critical nominal tensile strength, and the average of three sample size. The obtained value are close to the value obtained by Asadi et al. But our model has a more solid physics and mechanical foundation. Part 5. Conclusions. In the quasi-statical loading regime and in the dynamic loading regime, the formulae for the coupled effect of sample size and the strain rate on local tensile strengths are obtained. The above formulae are superposed to obtain the unified formulae for the coupled effects of strain rate and sample size effects on local tensile strengths. The critical strain rates and the critical sample size are determined. The compilation of the theoretical protection with experimental result show good agreement, indicating that the proposed model is reasonable. This is the end of the report. Thank you very much for your attention.